Today we're going to talk about reaction mechanisms. When chemical reactions occur, they don't occur in like an all at once reaction. There's always a series of steps they go through. When you're talking about forming water from hydrogen and oxygen, there are a series of steps that take us from diatomic hydrogen and diatomic oxygen and allow us to form two molecules of water. This series of steps is called a reaction mechanism. Now, some people spend their lives trying to determine what the reaction mechanism is for a particular reaction, for one single reaction, because we can't actually see the molecules and what they're doing. But think about it. If that particular reaction was a reaction that caused somebody to have some kind of deadly reaction to there was some medical condition that was a fatal medical condition, and it was all hinging on this one reaction that was occurring in the body, and if you knew the reaction mechanism, maybe there was a step in there that you could provide a medication or provide an inhibitor for, and you could cause that reaction to stop in its tracks, and that person would be, saved. Well, that would be worth spending that time on. So it's very important for us to determine reaction mechanisms for many different kinds of chemical reactions. So these reaction mechanisms have these steps. These steps are called elementary steps, and the elementary steps are just a basic step. It's what happens, really, we think of it in terms of collisions. It's what happens when we simply have a collision between substances, either molecules or atoms. When we have an elementary step, we can write the rate law for that elementary step directly from its molecularity. Now, what the heck is molecularity? Molecularity is simply the number of species that have to collide to get that particular step to occur. For instance, look at this table. In this first one, all we're starting with is A, and A is just going to turn into products. Well, if that's all that's involved in that elementary step, then we're talking about rate equals K and just A. If, however, A and B have to collide, then our rate law is going to include both A and B. If two A's have to collide in order for this reaction to occur, then we'll have A squared. Or if two A's and a B, and these are really pretty rare because getting these to all collide at once in the right orientation is not common for an elementary step, but if they do, then we would have two A's and a B. So that's what we mean by determining rate law from the molecularity if it's an elementary step. We can't do that with an overall reaction. We've already established that determining the M and N values, the order of those reactants, can only be done experimentally for an overall reaction. Only for elementary steps can you determine it by its molecularity. So let's look at a complex reaction between nitrogen dioxide and carbon monoxide, and we can see that in this reaction, those two react and form nitrogen dioxide and nitrogen monoxide and carbon dioxide. From experimental evidence, we know that the rate is equal to K times NO2 squared, that evidently carbon monoxide is zero order, and the reaction is second order with respect to NO2. So we know that's true. We think that the mechanism involves these two elementary steps, that two NO2 molecules collide, and when they do, they form an NO3 and an NO. That NO3 then collides with the carbon monoxide that's in the container with it, and oxygen's transferred, and we get NO2 and CO2. So those are the two steps, elementary steps, believed to occur. Now notice something that appears in this mechanism that does not appear in the final reaction, and that's NO3. NO3 is what is called an intermediate, and an intermediate is something that is both produced and used up in the reaction. It starts out as a product, ends up as a reactant, and is used up before the reaction is finished. It does not show up in the final reaction. So that's our proposed mechanism. Now, how do we know if this is a good mechanism? It has to obey 3 rules. First of all, the sum of the elementary steps must give us the overall balanced equation for the reaction. They have to add up. Let's see if they do. Down here, we see that we've got this reaction. Remember, we've done this before where we've done this in Hess's law, if we have a substance on the right-hand side and the left-hand side of the reactions, we can cancel them. So NO3s are going to cancel, and one of the NO2s is going to cancel. And when those cancel, we end up with NO2 plus CO yields NO plus CO2. So there's our overall reaction, and it does match. So that part is good. The mechanism must agree with experimentally determined rate law, and it cannot include intermediate species. So let's see how that would play out. First of all, one of the rules is that if the rate determining step is the slow step, then we can determine the rate law from the molecularity of that step. Okay, that probably made no sense. First of all, because you don't know what a rate determining step is. The rate determining step is the slowest step in the mechanism. Think about it this way. If you were running a race, then you are limited if you're running a relay race, or for some reason you're running a race, you're going to run a 100-yard dash. 4 people are going to hold hands and run a 100-yard dash. You are going to be limited for how fast you can run by the slowest person in the group. And that's the same way with our rate. We cannot get a reaction rate that goes any faster than our slow step. The overall rate can be no faster than the rate determining step. So that's the definition for rate determining step. Now we've got this first step here in our rate mechanism, or in our mechanism for this reaction, as the slow step. What does that mean? It means that we can use just what we start with, just the reactants of that slow step, and determine the rate law by the molecularity. Remember, that means that rate is equal to K, and since there are 2 NO2s there, that's going to be the rate law based on the molecularity of that first step, which matches the experimental rate law. And the rate law does not have NO3 in it, so it does not have the intermediate in it. So it obeys all of the rules. So we would say that this is a very good candidate for the reaction mechanism for this particular reaction. Let's look at another one. This one wants us to find the overall reaction and the rate law for the following mechanism. So let's look at this. First of all, we're going to cancel anything that can be canceled across the arrow. So it looks like we're going to be able to cancel 2 I's with our I's on the left-hand side. And it looks like H2I's can cancel as well. So both of those appeared as products in the reaction and then got used up. So hopefully you would agree that both I and H2I are intermediates. Okay, so the first thing then that we would look at the rate law for our slow step. And the rate law for the slow step is that rate is equal to K. We're using only the reactants, H2I times I. Now, what's wrong with that for a rate law? Well, both H2I and I are intermediates, so that's like doubly wrong for the rate laws. We can't use either one of those. So how are we going to solve that? And we should have known that that wasn't going to work anyway, because the slow step in this particular reaction is not the first step. The slow step is the last step. So we're going to have to use information from the previous steps in order to solve this equation. So what we want to do first is just to write what the other reactions would be as parts of rate law. Remember, one thing you need to realize is that if substances are added in a chemical reaction, they're multiplied in rate law. So this second reaction right here, we're doing this reaction right here, I times H2 equals H2I. Okay, now I am going to totally redo that because that just looks horrible. Can't even read what it says. So let's try that one again. Okay, I'm going to do it this way. According to that second reaction, I times H2 equals H2I. Remember, like I said before, if it's added in the reaction, it's multiplied in the rate law. So that's what we can say from this reaction. We can also say from the reaction above that, that I2 is equal to two I's. I plus I, which really means I times I, right? So that's what we've got so far. And what we're going to have to do is to substitute in information from previous equations until we can get rid of these intermediates. So let's get rid of H2I first. And we just go one reaction at a time. We're going to try to get rid of H2I. And right here we said that H2I was equal to I times H2. So let's plug that in. So H2I is equal to I times H2, and we still have the I from above. So that's what we've got so far. Still not a good rate law because we still have I's in there and we can't have I's in our final reaction. So what are we going to do next? Well, we've got to get rid of those I's. And our top equation says that if we have two I's multiplied by each other, so those two I's multiplied by each other, that's going to give us our I2. So we can take this I and let me do this in a different color so hopefully I'm making it make sense. This I and this I, so I times I, and we can substitute those with the I2. I times I is I2, so we can substitute that and say that the rate is equal to K times the I2 times the H2 that's still up there in the reaction right here. So now that we've used up both of our earlier reactions that occurred before the slow step, have we got everything in a form that will work in rate law? And both I2 and H2 did show up in the final reaction. So this is a good rate law. Okay, now the last thing I want to do is to look at this one. This one is a pretty interesting reaction or problem. It showed up in on the AP test. I want to say it was 3 or 4 years ago, and it kind of threw a bunch of people for a loop. I know I hadn't seen this particular order of a reaction before, and you'll see what I mean whenever we get through with it. The first thing I want to do is, first of all, ask if CH3 is Cl is a catalyst or is it an intermediate? Justify your answer. Well, in order to really determine this, let's go ahead and figure out what our overall reaction would be. Let's see what happens here. Looks like this Cl, that we're going to be able to cancel Cl's here. Looks like we're going to be able to cancel Cl's here. So those are canceling out. We've got a CH3 canceling here and here. We've got a CH3Cl canceling here and here, and H's canceling. Can we cancel anything else? I can't see anything else that will cancel, so what we end up with is Cl2. In fact, there are two Cl2s here and here, plus CH4, forming, looks like we've got two HCl's here, plus CH2Cl2. So there's our overall reaction. And it looks like our CH3 then, the target substance that we were asked about, is produced in the reaction and then used up. Remember, if it's produced in the reaction then used up, it is an intermediate. So CH3 is an intermediate. It is produced and used up during, in the middle of the reaction. Okay, so that answers that question. The next question says that it wants us to identify the order of the reaction with respect to both CH4 and Cl2. Okay, so we look for our slow reaction, and our slow reaction is right here. And according to the slow reaction, it says that rate is equal to K times CH4 times Cl. Well, what's the problem with that rate? Well, that rate law can't be a valid rate law because we have an intermediate. We cannot have Cl in that rate law. So we're going to need to replace the Cl. So let's look at the only other reaction we have to look at, which is this first one, and let's rewrite that. What that says is that the concentration of Cl2 is equal to the concentration of Cl plus Cl, which is the concentration of Cl times Cl. And if you think about what that says, it's saying that the concentration of Cl2 is equal to the concentration of Cl squared, right? Now here's where it gets a little iffy. We don't want Cl squared, we want just Cl. So we're going to need to take the square root of both of these to get rid of that squared. So when we take the square root of both of these, we end up with the fact that Cl is equal to the square root of Cl2. Here's the problem. They won't let us use a square root symbol in a rate law. It's only exponents that we're able to use. And do you remember what the exponent symbol is for square root? The exponent symbol is that Cl would be equal to Cl2 raised to the 1/2. So we are going to be able to replace this Cl over here with Cl2 raised to the 1/2. Rate is equal to K CH4 times Cl2 raised to the 1/2. The first time I had ever seen a half order or a reactant that was half order. So this is half order with respect to Cl2. So 1/2 order. And we explained this. I'm not going to rewrite it. The justification was the mathematics we used above there to determine our rate law. So it's half order with respect to Cl2. I tried to Google that and I ended up with half orders of French fries and half orders of onion rings. It didn't tell me what the half order was, but the half order with respect to Cl2 and it was first order with respect to CH4. And we just got through writing the rate law for this reaction, but I'll write it again. Rate is equal to K CH4 Cl2 raised to the 1/2.